I think the beginning of today, we tried to set up a fairly wide view of saying computation, pattern prediction, new systems are what we're trying to go after. And again, there are neuroscience reasons for it, and there are applications reasons for it. And we did see a very broad cross-section of that today. Maybe I'll go ahead and start on the other end of the table with Lloyd, and then just maybe 1 or 2 minutes in terms of what you've seen today and some of the things that have stood out to you, maybe you'd like to highlight or maybe kind of seed the discussion with. And then we'll do that through the panel once through, and then we'll open it up to the audience for Q&A as well.
But for some reason, the thing that stands out for me was in Karl-Heinz Mayer's talk, just the scope of the time scale of the project, the 10-year time scale from beginning of developing their chips to having their functioning systems and maintaining the continuity of funding and effort team through that whole process. And similarly through Dharmendra's talk as well, just seeing the massive scale of these huge projects. To me, that's tremendously impressive, since obviously I'm coming at things from a single-person startup company with such light funding. So that's one of the things that's struck me in today's talks.
Actually, just coincidentally, wanted to ask the same question: is why does it take so long when a small company can do it in 2 years? So I think it's a more complicated technology. There's analog components and so forth. But I'm a neuroscientist, and we're able to start a company, hire the right people, and build a processor. Hopefully, it's not finished, but within 2 years, 2.5 years. It's nice if the cycle of technology is faster. That's really useful, because by the time you're done, your chip is potentially obsolete.
Maybe just a quick comment to that very similar pattern. Previous speakers in previous workshops have commented on that. For example, Dan Hammerstrom had a neuromorphic chip startup, and that has been the experience that once you build the chip, design the chip, and get it out there, CMOS, sort of the Moore's law, had sort of steamrollered over what those improvements were. So I think that's been sort of a common experience, but it might be changing now, because now the Moore's law or Dennard scaling has saturated, and there is actually a lot more value, a lot more capability that can be extracted from some of the new things that this crop of neuro-inspired or new systems might be able to harvest. But again, that's actually a very, very important point that has attracted some attention.
Well, I'll change a little bit. I think from the more science side of it, what was interesting about today's conversation, and it came up in Bruno's conversation with regard to Christoph, and the question that we've talked about a number of times at NICE is, and it's the field in general, is how much biological detail is necessary. And I actually think this relates to the previous points. And, we don't know what the right level of abstraction is for the brain, and to understand its computation at all, and then much less implement algorithms and hardware. And we have, we've heard a couple of cases from the folks on the left of me here of pick a certain approach and go for it, build hardware, and you can do it. But if you want to have this more bigger picture, large scale, any sort of neural algorithm, do you need dendritic computation? Do you need neuromodulation? Do you need 5 different types of plasticity, or is one version of STDP enough? And I go back and forth. You can wait for the theory to resolve the question, but then you don't get anywhere. It's like that could take forever. You need to actually have some intermediate steps being built. But at the same time, do we actually know enough to make substantial inroads? So I think we're at an interesting place, because we're actually getting both going on at the same time. We're getting some prototype hardware, and we're getting some real inroads in the theory, and I think it's a neat place to be.
Yes, so I was about to make a very similar point, so I'm just going to take it a little bit further. But while I was presenting the benchmarking results today, my background and most of the work in my group that's ongoing is in computational neuroscience. And as I said, I was about to bring up this point of how much detail of what we see in the brain do we need and which elements of that detail do we need. And we had the great example of the eyes, and we had with other mentioning of the dendritic computation and so on. And I think that the next step in trying to answer that question is also to first ask the question, how can we choose that? How can we make an inroads to what's important and what's not? And I think we had a couple of those pointers today as well in terms of talking about closed loop systems, neurorobotics. And I think in terms of being a computational neuroscientist, it's important to get all the way to the behavior, to have something to base the theory or the predictions, what is important and what's not on. Because if we can build models that go all the way to the behavior and then can be benchmarked against psychophysics or whatever the experiments might be in maybe a robot, then maybe we have a better handle on what's important and what's not without having to resort to just trying everything out.
Okay, I mean, two things. One is an answer to the question, and the other is my personal impression of the presentations. The answer to the question, of course, I mean, making a chip is fast. I mean, you do the design, you submit it, you get it back, you test it, and it's done. And that can certainly be done in 1 or 2 years. There's no question about that. But when Dharmendra and others develop these systems, it's really the systems. That means first you have to think what you want to do. All right, and you have to understand state of the art in neuroscience. You have to understand what's worthwhile to implement. You have to make good guesses, for example. They may be wrong, they may be right, and that takes a while. You have to run simulations. Then you have to start producing hardware at some point. So there's this little piece of silicon, but that doesn't make a system. I mean, you have to make the boards, you have to make the power supplies. You have to assemble this into something that is solid so that it can be used by a general user. And then there's something else. This is a new computing architecture. And that means all the software you need to operate it, to configure it, has to be written. It has to be invented. Nothing like that is available. I mean, imagine you are the inventor of an FPGA. To make an FPGA is one thing, but it's only useful because there is the necessary software that goes from a hardware description to really the bit file that you load to your hardware. And that software development is a very, very major part of this time frame of 10 years. So at the end, it just took that time. I'm sure it can be accelerated. If you have a much bigger team, it can probably cut down now to a couple of years. But for this first go, it's just an experimental fact now that these three groups that work independently all used about the same time. And I tend to understand why that is. And that was my explanation. For my personal impression, I must say I was, once again, extremely impressed and most impressed by the talk of Christoph Koch. I really think this Allen Brain Institute is an absolutely remarkable institution. And what I said this morning is that it's very difficult to get our friends and colleagues from neuroscience to work in big collaborations. I mean, they have done it, and they have done it extremely well. I mean, they seem to have fun, they seem to enjoy their work, and they produce amazing results. I wonder why that is. I would like to understand that better, because I think that could be a model case also for other projects. I won't name them now, but I mean, clearly there are big projects that have more problems than the Allen Brain Institute. And so I was really impressed, I must say.
So maybe just one really quick comment in terms of why it takes so long versus maybe it doesn't take so long. I think, Amir, the system that you guys were able to put together is very deeply focused on machine learning, deep learning, and there's a very clear-cut case for what functions, what kind of a system is needed, and I think that probably sped up that process quite a bit also. Just quick observation. But
well, a couple things. First, I was really struck by the breadth of perspective, the two opposite ends of the spectrum of perspective of the two first early talks this morning. One was Amirs describing the extraordinary level of activity in his company, building a both algorithm and then perhaps eventually a hardware system for turbocharging deep learning and then making applications. This is not very neural, and as a PhD neuroscientist himself, he'll be the first to say so. It's, however, very powerful, and it's sweeping the world in terms of commercial application, and it will continue to. And then the other end of the spectrum is Christoph describing the extraordinary, beautifully managed depth of information to really appreciate and catalog the complexity of neural circuitry. That is a huge gap. Bridging that and finding things that are truly neural that can be integrated into machines is, of course, has always been the mission of this series of conferences. And it was really made very crystal clear in comparing, I thought, those two talks.
Yeah, I guess I'm intrigued by these efforts to build spiking neuron chips. And it seems like a good direction in terms of incorporating mechanisms we know about in biology and seeing what they can do computationally. And I guess I'm still personally wondering, where, when we're going to be able to show what unique properties a spiking system has that you couldn't do with another kind of system. And I guess I'm thinking of one example, like Chris Eliasmith's brain model, which many of you probably know, the Science paper. It seems like you could take that kind of model and replace all the neurons with just sort of analog valued, rate neurons, and you'd have basically the same functionality. And so it seems like, I guess deep down, I feel like there should be some unique properties of spiking neuron systems that only a spiking neuron system is going to have, and you couldn't have in an analog system. And I'm just kind of personally wondering where that distinction lies, or if it exists yet. But I'm intrigued.
Hi, thanks. I'm Tom Cleland, Cornell University. So in some ways, if there's a first principle to biological neural systems, it's heterogeneity and diversity. I mean, this is really prominent in sensory systems where certainly primary sensors, but also the follower circuitry are pretty much adapted towards physical features and other properties, desirable extractables from the sensory variants that they're aimed at. In other words, these are very specialized circuits for particular purposes. And especially given that a couple of the themes that have been touched on by speakers this morning are about get circuits that aren't useful in the present context out of the way and you're more efficient, get out the graphic circuitry from GPUs and to design a more efficient convolutional chip, for example. Do you think, in each your own way, that at the very least the first generation, but perhaps as a general rule, the useful neuromorphic chips, the really commercially valuable neuromorphic hardware are going to be application-specific circuits, as opposed to trying to replace general-purpose computers with neuromorphics?
Well, so I would say that both are if you call the convolutional net specialized chips neuromorphic, I don't think one would, but they'll certainly be useful, and they're being specialized is key to the 100x improvement in power and performance that Amirs is gunning for. But I think that true neuromorphic chips, to really do what Bruno's suggesting and integrate neural mechanisms and see what they can do, they have to be programmable in the way that Karl Heinz's group has worked very hard to make them, where mechanisms can be introduced or shed, and of course parameters of all sorts, not just weight changes, but time constants of synaptic activity and synaptic short and long-term plasticity. And we're in the business of exploring the interaction of the very complex interaction of mechanisms, and so the neuromorphic chips need to be able to support that exploration. And I think that's exactly what Karl Heinz's group has achieved in the generations of chips that he's. So they would be. My answer would be as flexible as possible, because we're in the business of exploring the interaction of mechanisms.
Yeah, I mean, it's in particular the lack of really reliable and generally accepted theories that stops us from making very specific implementation. And of course, my hope is that custom chips in the future will design themselves by using the previous generation. If you have very configurable systems and theoretical ideas, then you can use the configurable systems to explore parameter spaces and then come up with good solutions. And those solutions then can be extracted from the prototyping systems. And those circuits and their parameters can then put into specialized custom chips. That's the dream. It hasn't been demonstrated so far, but I think it's an attractive way. So we are using the neuromorphic architectures themselves to come up with optimized solutions.
So
So
it's
like rapid prototyping.
So I'm hearing a lot along the lines that, you know, the trade-off of flexibility for efficiency is sort of exactly what I was referring to. If you want sort of end-use chips for purposes, then this would come at the tail end of the sort of prototypes and the iterative design, so that in the final, the most useful, most cost-effective hardware is no longer, doesn't have the flexibility of a prototyping system anymore. Which you could say that wasn't the case for our current computers.
Well, one thing, I guess, and this gets to Karl Heinz's point about theory. Once you have a really good theoretical basis for the architecture and the algorithms you're building on, I don't see a reason why you can't take something like a true north chip. If you really understand the theory around the spiking systems and maybe if there's learning embedded in it or whatever, but then go from that to a large number of algorithms so that you kind of close the loop going back into algorithm space and say, I understand what the chip is. I have a theory of true north computing, for instance, or spiky computing or Spinnaker computing or whatever the generation is a few from now. And then redesign algorithms that fit that. And that's basically what's happened with GPUs and CPUs and so forth, where the algorithm design ends up fitting the architecture. Right now we're trying to squeeze von Neumann algorithms onto neural architectures. Of course it's not a great fit, but eventually the architectures will inspire the algorithms, and the algorithms will inspire the next generation of architectures. So I think we can actually have impact earlier than kind of what you're saying, where everything has to settle down. I think it can be a lot faster.
So, Tom, let me take your question. First of all, good to meet you after so many years.
Pleasure.
So I think that there are two approaches. Neuromorphic, first of all, it's not some sort of a label or some that we're trying to earn, right? There are two approaches. What Karl Heinz is pursuing is he's sort of building an experimental instrument, so as to say, which to enable, much faster than real-time exploration of hypotheses and supporting scientists and network discovery. What at least I have been thinking about, is we are trying to extract insights from the brain for commercial purposes, to be candid. And when you are trying to do something for commercial purposes, it comes down to just 4 factors. Is it really, is your chip lower cost? Means it's smaller area. Does it consume much lower energy? That means cost relates to capital cost, right? The area is capital cost, the purchase. Energy relates to operating cost. So certain operating cost is suitable for a mobile platform, always on chip. Certain operating cost is suitable for a data center. Now data center space is much more a premium than power often. Third is the throughput, right? How many frames per second you can get. Now, if you're, for example, if you're a government agency, or a humanitarian agency, whatever, and you're surveying a disaster area and you want to find something very quickly, throughput is important. And the fourth thing is the capabilities. Is what can you build? What applications can you show within space, time, and energy constraints, right? And what happens really is that oftentimes, as we are going to neuromorphic, really, it is not fundamentally possible to recreate the brain because we do not have the biophysical, biochemical, technological substrate. We don't have a 3-dimensional cortex-like substrate. So all we can do is look at the image of the brain in the mirror of the silicon. Poor mirror. And then within that, how do I play with time, space, and energy to make the capability remain high? That's where the trade-offs come. So if you look at the 3 approaches that Karl Heinz and fervor, I, nirvana, it doesn't really matter. You throw in any architectural approaches, it's going to be trade-off between these four things. And so that's really what it comes down to. And you can competitively argue, oh, that's more neuromorphic or less neuromorphic. It's more about what is it that you're trying to solve and what constraints can you live with.
Sure, absolutely. And I wasn't meaning to imply that nothing between here and some hypothetical application-specific chip, whatever. I've lost the meaning there. But it was more an idea of if the systems we're trying to emulate are characterized by their diversity of approaches to diverse solutions, then is sort of the logical limit of our efforts going to lead us inexorably to diverse solutions. And of course, I mean, I think one of the points you've embedded in your comments is that a system like True North does a lot of things different than a classic von Neumann architecture, and given the development costs of a platform that works, it's unlike, that's one reason you wouldn't go and build everything highly specifically, because this is a good medium between one platform, diverse applications, and a local minimum for cost performance.
Yeah,
I'm going to stop hogging the floor here, but
yeah, I mean, that's another thing. So that's a fourth. So, time, space, energy are the physical constraints. And capability is, are you really building a substrate, or are you building a very specialized architecture? And then again, you can trade off better. It's just engineering.
There's more a question about the the limits as this type of work progresses into the future. Anyway.
Sure. I just have a comment sort of directed at Bruno. I thought it was a great talk, but I wanted to just add sort of another dimension to it. So when you think of, for example, you're talking about active dendrites and or nonlinear dendrites, and how this can be, somehow, a better way of building models. And so, there's two ways of building better models. One is that, given some sort of task, like whether it's performance or some data set, that you could actually do better. And the other is that, it's lower energy, it's a better sort of substrate for doing computation. And so I think those things are often conflated. And, if you look at sort of the trends in deep learning and sort of read the tea leaves, it seems like whatever task you throw at it, deep learning is going to probably be ahead of the curve, because, it's just a general function approximator and really good nonlinear optimization. So you could probably do better in tasks using deep learning. So, is the idea that these new components are actually going to get us better than the performance of deep learning, or is it more of just an implementation that the brain has found really efficient ways of implementing sort of this nonlinear, transformations that are being done? And if separating those two ideas out sort of get you, maybe the dendrites are just an efficient way of implementing, multiple layers of feed-forward neural networks, for example. So
I guess the way I look at it is it's a more powerful computational device, the actual biological neuron, as opposed to the neurons we're using now. So the neurons we use now in our models, they're actually quite impoverished compared to what real neurons can do. And so if you can do more with a single neuron, then why not do it? And I guess another, sort of line of thinking there is just adopting the Carver-Mead, philosophy and approach, which is to try to exploit what the natural physics of the computation gives you. So for in silicon, sort of exploit what the NP junction naturally gives you, this exponential current voltage relationship, and see what you can do with it. And then the same thing in the biology. So if the biology just naturally gives you these nonlinearities and you can compute with them, then why not do that? It makes sense. So I think that's the sort of angle I coming at it from. And as in terms of like, someone else was asking, like if you could, like in the Bartlett-Mail model, you could just sort of conceptualize a single neuron as a multi-layer neural network, and then so now you could just sort of, you could take your deep learning neural network and then just repartition what you call a neuron in it, and then maybe it's the same thing. Maybe that's so, and I guess it might come down to implementation. So it might be that implementing these devices, and it matters what the device physics is. If the device physics gives you something more natural that you can do like that, well then go ahead and do it. I guess maybe another sort of way of looking at it is you wouldn't necessarily want to break your back to build a linear neuron that does, inner product. This is something I keep on beating Amir on. So this is like, it's just
Among many other
because there's nothing sacrosanct about, computing inner product and a threshold. That's just something we came up with 50 years ago, and we've been sort of stuck with it ever since. And so if something in the computation, if there's an easier way to do something else, well, then I would just do it. That's what I'm trying to sort of say is that neurons don't do that anyways. So there's no reason to stick with it. There's nothing fundamental about that computation. And so we should sort of free ourselves up to think about other computational primitives.
If I can add one more comment to that, I really liked you brought up that question. Now he's leaving. No, that's all right. But I just wanted to add, I think you have raised a really good point there, that brains have evolved to be good enough to do things. So whether they have to be deep learning is a very valid question. So in the end of the day, if you think evolutionary about it, then a human has to survive, has to reproduce, and not be 99.999% correct on pattern classification tasks. So I believe there is some point where we need to be clear about our goals. We need to be clear about the goal. Do we want to be this 100% perfect, or do we want to do it like the brain? Because the brain's not going to be 100% perfect. And you can look at human performances on these benchmarks, and they're typically not as good. So I think you raised a very valid point there. And we need to think about the other side of it. How efficient is it going to be?
I'd like to go back to a comment Bruno made in the opening comments about spikes. And why would we want spikes? What are they doing that are special for us? And just to throw out a thought, what if the job of spikes is nothing more and nothing less than to move a signal from one point in a physical system to another quickly and reliably, and that anything else that would do that would be just as good for us?
Well, I guess the judge is out on that question. It's definitely possible, but then there are ideas where spike time independent algorithms have been formulated that are quite reasonable. So I would say the jury is out. We'll find out when we find that algorithm that's really better than the rate-based one. And if we don't, then that's our answer.
I mean, I think that's a null hypothesis that should always be the most parsimonious, at least considered, which is that, that problem needed to be solved to communicate the output of one neuron to 1,000 or 10,000 targets sufficiently rapidly, and that's a biophysical mechanism to do that. And so that the answer that you're posing, which is a very lucid one, is that that's what spikes are for, is perfectly sound, and there may or may not be additional, and there probably are additional computational leverage. Once that evolved for the purpose of transmitting information, there may have been further leveraging of the phenomenon of spikes for computation that couldn't happen without it potentially, but that may very well be the basis, the dominant basis for their existence.
I'd also add that it's worth separating spikes going down axons for communication purposes and the sort of nonlinear, forcing computational neuroscientists to think about spikes is a good, useful way of doing what Bruno's been suggesting, and that is not make everything a sigmoid. So I think spikes force, I think it is spikes are adding a very powerful nonlinearity to the computation. And I think someone talking earlier was basically pointing out that is the computation, is the nonlinearities. So I think we should separate out that part of the spike. There is a computation going on there as well.
So there's actually a book called Spikes by Bill Bialik and David Worland and Rob Droider, Van Stevenik. And one way they in that book, but they sort of the way they think about spikes is that they're a sparse code in time. And I think that's an interesting link to sparse coding. And when you learn a sparse code in time, so when you take this whole idea of sparse coding in the time domain with dynamic signals like sound or video, then what emerges from that is something like a spike code, because you have basically long stretches of zeros and then a few events, which are kind of punctate. And one thing I'm kind of intrigued by is if you started to put energy considerations in that, because that's something we never sort of include in our optimizations with sparse coding. But if you put in an energy... I'm sorry? Add that as a third attribute. Yeah, that's right, exactly right. If you add that as a third term, then maybe that sort of starts to... then you see these, maybe you would see something like spikes emerging more like, like a 0-1 kind of spike. So something I'm intrigued by is ideas we've played with, sort of thought about that, but we haven't done anything along those lines.
Just to add to that, as someone that's building sensory motor processing systems, spikes is the most natural thing to do, because at the sensory periphery, that's what you need. I mean, I'm sure everybody agrees that for ITD, spikes are the most efficient representation. Then maybe by the time you get to inferotemporal cortex, you need to, parietal cortex and so on, you need to integrate and look at mean rates. But using spikes allows you to have both representations at both levels of the system. So if you're trying to build a whole system that's both processing data at the sensory periphery and using that data at the higher processing areas, spikes are the most natural thing to use, in addition to being able to communicate signals across long distances and being efficient in power and so on. So if you really think about it and you want to build a system that actually works efficiently, that's the most natural thing to do. And going back to the chips, I think the first, I don't know where Paul is, but the next, if I were to build a startup, I would try to find a niche application that uses very specific chips. Brains are not general purpose computers. Brains are very specialized. We need to reproduce and survive. We don't need to classify or do bank accounts with 100% accuracy. So I would look for IoT or brain-machine interfaces, things that require low power sensory motor processing. And there this technology, whether it's analog or digital, might have some chance of beating GPUs and the types of chips that you're beating in deep learning architectures.
Just a comment there, you say brains are not general purpose computers. What Christoph Koch said this morning is contrary to that. I mean, he says that if you look to the structure of the cortex, it's kind of uniform across species, and even within the cortex, there's very little specialization. So the cortical structure of columns and layers seems to be a rather generic information processing and even controlling device for motor action. So I think it's probably worthwhile to look into this architecture as a rather generic computing device.
No, I perfectly agree. I mean, I come from the Cortical Microcircuit Institute, Rodney's and Kevin's. I know. So that's my religion. But this common architecture that's the same at the macroscopic level throughout visual cortex, somatosensory, auditory, olfactory cortex is very specialized. It's not like a von Neumann architecture that can be programmed to do many different things. There are very specific functions that it has evolved to do most efficiently. So that was so there is a little bit of both aspects in human brains, but it's not as general as a von Neumann architecture.
On a slightly related note, I think it's very exciting the ways that people are thinking about flexibility and the resilience that we see in neural circuits and in brains, but there are also kind of very specific limitations that I think are also worth learning from and possibly trying to surpass in terms of like the decrease in flexibility over time in neural circuits, the fact that you get biases that are introduced, you get things that can be learned early but not later. And I guess, are you thinking about ways to learn from these limitations and these failures in neural systems and kind of improve upon them?
Well, I think it's a great attitude to not simply seek to emulate the capability of neural systems, but why not build machines that are far more powerful? I mean, first of all, that's just a good attitude. If you think about the facility with learning early, critical periods where you can learn language just by listening to it, all that maps to developmental, there's a whole branch of neuroscience, developmental neuroscience, where you've got perfusion of synapses that then get, and axon and dendrite branches that then get pruned back, and there still is continuing revision. possible, but once that profusion and pruning happens, that revision is more limited, and so it's a great topic of study. I mean, would you want to build a simulated system that would have multiple epochs of profuse growth and pruning back? Great thing to explore. You should do that.
So I'll add, I mean, the interesting challenge with learning is that you don't always want to learn. I mean, in machine learning, you have a stability plasticity dilemma. So there's some things you want to learn and some things you don't want to change, right? You get one event comes in and it challenges your classifier. Well, maybe you don't want to rewrite your classifier for that. And so you could argue that, as Paul was talking about development, we accept little kids making mistakes a lot more than we accept, adults making mistakes. It's just kind of evolutionarily, kids have adults looking after them. And so being able to tune that back and forth for a chip would be very valuable, but you have to be, I think, intentional about how you regulate plasticity. You don't always want everything learning all the time, otherwise you're not going to have a stable computation. But we need to understand this a lot better. It's an incredibly poorly understood concept, as I think Paul has talked about for a number of years here.
So maybe just to move the conversation in a little bit different direction. So looking at all the conventional computational systems, new techniques, algorithmic techniques that are emerging and actually are here, going back to the comment of how much biological or neurological fidelity do we need to put in there, and what's going to be the value proposition, what's going to be improved by the things that we're talking about here that some of the current systems might not be able to do, might not be able to deliver, and what, actually this was in previous workshops as well, sort of the value proposition. What do we need to show that is kind of the added value that says this needs to be done beyond what's at hand now? So maybe, again, from the panel and then also from the audience, if there are questions or comments to build upon that.
Well, I mean, one comment I would like to make is that putting in biological detail as a capability into these hardware architectures is always possible, but it's also always expensive in terms of time and effort. And the question always is, should we do it? I mean, just let me give you a concrete example. These are neuron models, all right? There are very fancy neuron models, like, for example, two-dimensional models like ADEX or Isikiewicz models. Most of the neuromorphic systems really are able to implement those neurons. When you see the application cases, many of them are just done with leaky integrated fire models, very simple models, and you get good results. So now we are there with our beautiful system, and I don't really see the application of the exponential term, for example, which took us a lot of time to implement. And there are other examples like that. Now there are the requests to put in structured neurons, and I understand some of the arguments, but what is important for us building these systems is that if you put it in, as I said, which takes a lot of effort and slows down the development of a system, that really people then make use of it. And it cannot only be the people that build the chip that use them. I mean, we are making them available to the outside world, and people should really then explore the capabilities. That's very important, because otherwise it's a waste of effort. It's always nice to implement things, but it's not being used and explored, then it wasn't worth it.
Well, if no one else, I'm waiting for Lloyd to weigh in. Here's a guy who built a neurally inspired silicon and put it to use in phones. Just where are neural circuits, where do they have utility? And how can we demonstrate that? So that was the theme of last year's workshop in some sense. And, the challenge from the convolutional net community, which is just burgeoning, I think, it has to be, a killer demonstration of a real neural computation would be a more truly neural circuit in the way that, however you like to define it, doing something that a convolutional net-based approach could not do well, or if it did, it would be at enormous cost in all sorts of ways. And I would think that that is going to be found not in the categorization of objects domain, or even the playing of Go domain, apparently, but in what neural circuits evolve for, which is to process continuously streaming sensory information to control sensory motor behavior embedded in a complex environment. Now that may be a task that isn't needed in most industrial applications at the moment, but that's what neural circuits evolve for. And presumably that's the most natural place to look for challenges that other forms of computation couldn't match. And of course, ultimately, one has very cool machines, autonomous robots that can navigate in complex worlds that would be enabled only by neural circuits. And that application space would be the place to prove neural circuits superiority the most natural way.
Can I ask a question? So I think the discussion was extremely interesting, and it was pointed out that there are many ways to judge actually the quality of, let's say, neuromorphic hardware and software which is being built. But now with the IT hat, I would ask the question, do you think that by 2025 we're going to have laptops without keyboards?
We kind of have them already, and then we kludge a keyboard onto them, but
Can someone rephrase the question?
so maybe rephrasing the question. By 2025, will we have low power enough processors that can do natural language processing without having to go hook back up to the cloud and provide you with the information that you need?
Well, I mean, the Google Glass language processing is not on the cloud, right? And it's not bad. I've tried it out. You can dictate it, and it gets most of the things right. So I think in terms of natural language processing in the computer, that wouldn't be necessarily such a high benchmark. But would it be neuromorphic by 2025? That's the question I would ask. So would your chip in your laptop be neuromorphic?
I mean, I'll maybe kind of jump a little bit on that. I have found that if you can define a problem very cleanly, like what you just said, or what you were saying, we can come, maybe not we as an I, but engineers are able to come up with solutions if the problem's definable. A lot of the problems that when we talk, when we talk about where neuromorphic's going to make applications, is it's actually kind of hard to define the computational problem very cleanly. We want to have a robot navigating through a room and open a door. That's a very under-constrained definition I just gave there. And so it's a challenging problem. If you say I want a, robot that can climb stairs, someone showed an example of that this morning. So I think the ability to define a problem very cleanly is a very key aspect of this engineering. And neuromorphic, I think, suffers from that problem.
So I'm no expert in quantum computing, but what I can understand is that this technology offers potential to tackle some of the same problems we're trying to tackle here, which is extracting information from high-dimensional data. And I'm just wondering if you have thought about or see any opportunities for synergy, either conceptually or implementation-wise, between neuromorphic ideas and quantum computing.
Well, I mean, true quantum computers require the implementation of entangled states, for which you have to create very special conditions, in particular, usually low temperature, and only very few devices are able to do that. Complex error correction mechanisms, all these things are not necessary for neuromorphic computing. So in terms of hardware, I see very, very little overlap, actually. It's a completely different approach. A brain is a classical complex system, and a quantum computer is an entangled set of of objects. So there is no similarity. I actually talked to the D-Wave people, and I visited them. I looked at one of their machines, which looks very impressive. What I found interesting is that they have the same kind of approach to software. I mean, also these systems need to be configured. And I mean, this is an adiabatic quantum processor. It's not working so much with individual, or not working with individual qubits, but really does some kind of energy minimization, which is similar, for example, to Boltzmann machines, of course, with different aspects of quantum physics. But the software they develop to configure the system, to read out the data, to analyze, and to feed the results back into the machine, that I found very, very similar to the tools that we develop. And I think there could indeed be synergies, but they would be purely methodological. I mean, I think there's no deep relation between the two approaches. But in terms of software services, for example, I think there are similarities, which I found quite amazing, actually. For example, they solve problems like the traveling salesman problem or Sudoku or whatever, and we try to do the same thing, of course. You hear a talk tomorrow where you see that you do the same thing with neuromorphic computing systems. So describe the problem, upload it, get the results back. That's very similar. And you have to develop those special software tools.
So maybe from the panel, are there any other topics that had come up? Lloyd?
So there seems to be a theme underneath some of the questions about neural hardware and what will it take, or will we see neural chips that were designed in some neuromorphic way, somehow entering the market and becoming important. It appears right now that there's a group of companies, Nirvana being one of them, that are trying to do deep learning acceleration. That seems to be one near-term opportunity for commercial deployment of chips that could really find a niche in the market and get sort of a permanent foothold. That, you know, it's not that hard to come up with an idea about a thing that would be useful to do, but raising the $70 to $100 million to get it off the ground and then finding a market that's big enough to pay that back and stay alive long enough. I have some experience doing that for some time and then not doing it eventually. I mean, hanging on to that market long enough to stay alive permanently, that's a pretty good trick. Getting started is one thing. So deep learning acceleration is emerging as an interesting category with quite a few entrants in the market trying to attack it, which unfortunately means dividing up a pie which is not yet that big. So, that's tough. Another entrant in the market that struck me as doing something different is Movidius. Now, that company appears to have been doing something analogous to what Audience tried to do. So for those of you that don't, my history there was building a chip to accelerate audio understanding, sound understanding. So unlike rendering, it was trying to sensory input and build a pipeline that could accelerate that. And it looked like there might be some permanent role in mobile or phone processors for hardware acceleration of that sensory processing pipeline. Movidius appears to be doing the same thing, but for the video processing pipeline. And you could imagine, okay, scene analysis of your camera, having that hardware accelerated would make just as much sense as NVIDIA hardware accelerating the rendering pipeline. So that, to me, that makes sense. But now, what I'm seeing there, so that looks like a sensory processing pipeline could have a permanent, as Giacomo said, sort of a specialized role that would allow it to stake out as a permanently useful attribute of, say, a mobile phone or some kind of processor. So what I'm seeing is two places: sensory processing baked in as a hardware accelerator, and the learning part baked in as a hardware accelerator. So those two look like potential candidates to have serious market traction, enough that they could actually get to critical mass And then, hold on, so, presumably all 10 companies that are trying to compete in that space aren't going to succeed, but there could be one winner or, one or two winners, and I hope that our colleagues will pull that off. I mean, it's, to the victor goes the spoils for achieving that. But those are the two places that I see: hardware acceleration of learning and sensory processing, specialized sensory processing that have the potential to become permanent fixtures that you could say would be neuromorphic type chips, at least neurally inspired chips. If anything, the high level comment, having developed a company that did hardware acceleration of the audio pipeline, in order for that company to succeed, you have to raise $70 million, and then you have to go get a market that's big enough to justify paying that back. And there's only one market that's big enough to do that these days. It's the cell phone market. And here's the trouble. There's only two customers. There's Samsung and there's Apple. Now, if you get both of those customers, you win. Victory, Miller time, you get to go public, all kinds of great stuff happening. Here's the trouble. You lose one of those customers, and now it's like you're in a twin-engine plane and you just lost one engine. And you know what the other engine does for you? It doesn't help you fly. It just delivers you to the scene of the crash.
It's a bummer, Lloyd.
So if you're going to be in that market, go for it, but you better hang on to both of those customers.
I'd like to hear Amir's response to that.
So I guess we're still early on in this process. This is the first time I've done it. And you've been at it for a long time. I will face all the same problems that you faced. But one of the things that we did do is avoid the mobile market because it's brutal. It's very difficult to compete. The power budget on the phone is so little for doing computation that we went with the enterprise server market where it's very forgiving. NVIDIA has an awesome presence there. They have a great chip, but it's really painful for people in AWS and Azure to put NVIDIA processors in their data centers because they'll burn down. So given that setting, we're going to have a chip that's probably going to burn down their data centers as well, and they'll be tolerant of us as well, hopefully. That said, I wanted to comment on the technology that I saw at the Telluride workshops. There is technology like the AR cameras and so forth that while I was working at Qualcomm, I pushed to get this adopted. And it's not so much a technology, but these large companies are so entrenched in their existing products. Qualcomm has to sell 750, I hope I don't get in trouble for saying this, but they have to sell so many chips to make things make sense. Intel is the same. Why should they use a deep learning processor? Why should they develop one? They have 99% of the market. It's not the technology that's not compelling. It's just these companies are just really slow, and we have to be either patient with them or I'm not sure what. I'd like to hear what is the strategy to get Intel that has incredible engineering, best process technology. Would love to build a deep learning chip with them. How do we get a company like that, which has 100% of the market share, to try this, or an IBM or another company? It's a little bit off topic. Sorry.
They are trying.
Okay.
All of the Samsung, Intel, IBM, they are trying.
Which one? The AR technology or the?
I mean, it's not top secret. It's known that they're all heavily investing in this type of technology, neuromorphic ideas and hardware development.
They are.
Yeah, Intel is, Samsung is, Huawei is. They are surveying the research institutions. They come to the talks. They get their own people hired, and they do have their own research divisions working on it.
So there's a third market. So we've actually been working very closely with Sandia for about 5 years, building a neuromorphic processor. We came out of stealth mode a week and a half ago. We actually started out where you talked about, which is speech processing.
and discarded it. So I have successfully done startups before, so I knew to get rid of it. The market we're after is cyber. And cybersecurity. And we have a working device that, as of a week and a half ago, you can order. Currently, it's implemented in an FPGA. It's 2 orders of magnitude at least better than current state of the art. And when we take it down to silicon, it's going to be somewhere between 10 to the 4th, 10 to the 5th times faster. Very large market, $100 billion market, desperate need. And so I agree with your comments, except there really is a market. That's the market we're going after.
Good.
So.
Good. Sounds good.